All right, so acids and bases, because chemistry is a party where everybody drops the base.
Acid properties. Acids are a very common group of chemicals that have a variety of uses. You see them in fruits, you see them in cleaning products, you see them everywhere. Okay, they remove rust, they're used in refining processes of metals, and they can do this because of their useful but sometimes dangerous chemical properties.
Now, before we actually get into the full discussion of acids, we need to understand where acids come from. Acids and bases exist in water. They have to be in water. Why is it that they have to be in water? Well, if we were to look at our little water molecule here that is on the right, water is a molecular compound. And normally when we break water up, water being H2O, we do not break it into H's and O's. We actually break it up because the molecule itself looks like this guy, right here. If I was to go and break this, I would actually end up breaking it here. And if I broke it there, the H's don't come off together. I would get an H positive down here and an OH negative up here. But it's important to note that while we are doing this, water is still a molecular compound. The reason that this is important is that water acts as both an acid and a base. Here's the acid, which means, oh, there's the base.
And as we mentioned in the previous video, we know that it's a universal solvent because we see both negative components and positive components, which plays into that as well. Just got to click the button there, McLeod.
I'm trying. Sometimes I click too many times, sometimes I don't click at all. Now, Arrhenius. Now, Arrhenius is fun because his name kind of sounds like he wants to be a pirate. Arrhenius defined an acid based on its behavior in water. He found that they all contained, that was the bell, it's currently going to fourth period. Basically what he found was that all acids, guys, had to have hydrogen ions. Therefore, they had to have H positive, which if you can read that, good for you. Regnier obviously cannot write.
There we go.
Don't worry, Regnier has it in the notes right there underneath. He just didn't get there yet. Ladies and gentlemen, all acids have an H positive. But all acids also must be in water, so all acids must be aqueous. These are two conditions to be an acid.
Okay, so let's look at an example, and this is exactly like we kind of showed before. All we end up seeing is when we put hydrochloric acid into water, which we see right here, HCl, okay, we see the water break it apart, and it forms its H plus and Cl minus ions. Okay, so since it is putting H plus in a solution, we end up seeing it define it as an acid. Okay, and we know this guy is aqueous, so we have met the two conditions of an acid.
Now, the other thing that will sometimes show up in here is that over top of the arrow, it might say H2O or water. All it's saying is that it happened in the presence of water. It's not actually a reactant.
Okay, so here is a point where you can pause the video and look at our wonderful list of common acids that we find all over in our workplace, at home, and in the school here. So pause the video, take a look, and make some personal connections.
Okay, so now that you're back, and apparently so are we are going to define a base. Now, a base, guys, in grade 10 is going to have all one common anion. It's all the same anion. It's the OH negative. Now, because the compounds that we will classify as bases have an OH anion, they must be ionic. So there's going to be some sort of cation put with our bases. Now, our bases are just like our acids. They must have OH instead of H positive, and they still must be aqueous. They still must be in water. NaOH is not a base. NaOH AQ is.
Perfect. Okay, another example. Okay, and again, we end up seeing this NaOH as a solid initially, but we know that it's in water like Mr. McLeod talked about earlier. So what that makes is it drops it into an aqueous solution. Okay, again, water breaks these apart right here, and we see our two ions form. We see Na plus and our OH minus, which means we have increased OH minus in our solution, and we have a base.
You're trying to sloppy as I do.
I do what I can. I'm here all week.
All right, so we have some bases that we're going to look at really quick. Now, guys, the reason that we glanced really quickly over the acid naming was because we have a whole section on acid naming. There are a lot of rules. For this one, they're just ionic compounds. So if you had to name sodium hydroxide, sodium is Na. Hydroxide is OH.
Good job, Mr. McLeod.
Because it said it's a base, I will add my AQ. Yes, you must include your states.
Perfect. Potassium hydroxide, same kind of thing. We look directly off the periodic table. We see KOH. I will include the aqueous.
That looks like KOA, and now I'm thinking about going camping. Now, calcium hydroxide.
Period 4 started. You're now late.
All right, calcium hydroxide. You're going to have your calcium. And, ladies and gentlemen, this is where we need to start being careful with our ionic. Remember, this was a 2 positive, and OH is a negative. In order to turn this into a compound, we have to be able to erase. We actually get CaOH2, and we still have the AQ.
All right, now we're going to deal with ammonium hydroxide. Same kind of thing as what Mr. McLeod just did. Ammonium we know as NH4. Okay, has a +1 charge. Okay, and now we have hydroxide OH negative. Okay, we got a nice 1-to-1 ratio, but we still need to make sure we include our brackets. NH4 OH, right like that. I'm sorry they keep merging together. Okay, now the only time you need to really include brackets in this situation would be as if you had more than one NH4. Since we have one, it's a nice 1-to-1 ratio. We can write them all in a nice pretty line. Woo! Done and done.
And now we're done.
Oh!
All right, ladies and gentlemen, so on to some properties of acids and bases. Now, despite what movies and TV may have told you, acids and bases, for the most part, are actually colorless liquids. They look just like water. So this first property, color, isn't really a property. But don't go assuming that, oh, that one looks bright green and dangerous. That must be acid, man. No. Acids look like water.
Now, with states, we've already talked about this before. Both acids and bases have aqueous states. They need to have that in order to be defined as an acid or a base.
Reactions with metal is a fun one, because reaction with metal actually only shows up with an acid. You don't need to understand why. Later, you'll need to know the reaction that happens. But for now, all you need to know is if the test is done where you put a piece of metal into a solution, if there is a reaction, it's an acid. If there is no reaction, it's a base.
Now, when we're dealing with litmus paper, there's 2 kinds of litmus paper, blue litmus paper and red litmus paper. Okay? If the blue litmus paper turns red and the red litmus paper stays red, we have an acid. If the blue litmus paper stays blue and the red litmus paper turns blue, we have a base.
Blue, base. But, guys, just really keep track of it. The other one that can be really fun is what happens when blue turns blue and red turns red.
Ooh.
If there actually is no color change in your litmus paper, you don't have an acid or a base. What would be halfway between an acid and a base?
I know it starts with an N.
Nigeria.
Oh, close. Close. We would call that neutral. Neutral.
All right, now, conduction of electricity. This becomes kind of interesting. Guys, your bases are ionics. So, this one makes sense. If bases are ionic, bases must conduct electricity. Acids, however, are molecular compounds. On a test, if you are asked, is acid molecular or ionic, you must say it is molecular. But they do have the ability to conduct. How is this possible? Well, if we look at any acid, acids have the ability to make H positive. Because they can make an H positive, they do have the ability to cause conduction.
Okay, and again, this is probably something you've already seen in middle school, pH. Okay, acids are obviously less than 7. Okay, bases are greater than 7.
We should probably just come back to that one. There's a whole
bunch of stuff on that.
Now, the last one's kind of goofy. Ladies and gentlemen, hopefully you know that if you take a base and react it with an acid, you'll make water. Or if you took an acid and react it with a base, you'll make water. We'll do more of that too.
The pH scale, the basics. Okay, the
Putty,
pH scale.
so putty.
Okay, the pH scale runs from 0 to 14, 0 being the most acidic and 14 being extremely basic. The pH of a solution is considered to be the quantity of H plus ions in each liter of solution.
Or of the OHs.
Whoa!
For a base.
And next.
Oops. Now, the pH scale, guys, the way most students we want to think about it, 0 to 14 is perfectly fine. If you want to carry on in chemistry, however, you need to know that the pH scale is actually just that. It's a scale. It does not stop at 0. It does not stop at 14. It's actually built around the number 7. In Chem 30, you get to find out why and how. Now, the number in 7 implies that H positive and OH are actually equal. So if H positive and OH are equal, they would make water. As you move away from 7, you either have more H positive or more OH negative. That would determine if you were an acid or a base. You can actually have negative pHs. You just don't want to touch them. Kind of turned out fuzzy, guys. Sorry, this is the first time we're seeing it on the big screen. Wow, that is fuzzy. So let's get down to what's really important here. Mr. Regnier, I would say this understanding.
Very, very, very important.
And now, okay, hang on. We don't need to worry about this middle part in here.
No, don't need. No, I don't think so. No, I think we're okay.
And we don't expect you to memorize a whole bunch of dumb things.
No, I don't think so.
So all we really need then is this little bit in between.
Yeah, just the pH. Perfect.
Now, lots of times, guys, your textbooks will show this as a scale, and this is where you actually get the idea. If you were over here, it is possible to be more acidic than 0.
Indicators. Acids and bases are usually clear liquids, like Mr. McLeod said. Okay, you don't go around a lab and assume when you see a clear liquid that it is just water. Okay, they usually look like water but are much more dangerous. Acid and base indicators change colors according to their concentration of H plus or OH minus in solution, which helps us tell what they are.
Now, indicators is actually a grade 11 topic, but you kind of briefly need to know how indicators are used. So we included a table of indicators just to show you some indicators that you might not have seen before. AKA, most of you know what litmus paper is. You know that litmus paper is red for acids and blue for bases. If we can scroll down on this thing,
come on,
there we go. Okay, we can see that there's actually, across the top here, a whole bunch of pH ranges. Down here we see a whole list of indicators. There are actually indicators that change at different pHs. The ones we're going to be most concerned with, perfectly, would be 7. If you want to really think about this as a scale, neutral can actually exist from 6 to 8. So we would have indicators like these guys in the middle here. These would indicate neutral solutions. The ones up here, those would indicate our bases. Everybody down here with the lower pH numbers, they would indicate our acids. The only reason we're telling you this, guys, is that if we give you an indicator like, let's say, bromothymol blue here, and it's going to turn color from blue to yellow, when it's yellow, that just means it's in the presence of an acid. You don't have to memorize these things, but we are going to work with them this year to start to give you guys a glimpse of what indicators look like.
Hint, hint, not judge. Oh, way to give away the answers, McLeod.
Yeah, well, I did that double-click thing again.
So indicators are pretty useful when used as a collective to help us determine the pH of a substance we're using. So if we as a class are analyzing 2 unknown substances that we see on the left, you can clearly see without our indicators, okay, we end up seeing
these are our solutions. They're colorless, so you can't see them on the black benchtop. You actually can't tell them from the empty dish.
Okay, now, if we look and we scroll down a little bit, if I can actually get this to work, there we go. We've added our indicators as shown by these wonderful arrows at the top. Okay, we have our 2 unknown solutions going across the sides. That's 1, that's 2. Okay, and we've used phenolphthalein on the far left, bromothymol blue on the middle, and methyl orange on the right. Now, what we're going to take a look at is how we look at these. Okay, so if we take a look at phenolphthalein, we have to find it on our list.
Here's our 7.
Okay.
Here's our phenolphthalein.
Perfect. So now what we end up seeing here is it's going to be colorless if it is less than a pH of 8. Okay, and it is going to be bright pink, okay, if it's greater than 10.
So when we do a lab like this, guys, you're going to notice that when it starts in water, it starts as colorless. It gets a color change because it's a base. Next indicator.
Bromothymol blue. Okay, we have to find bromothymol blue down on the bottom part of the page right here. Okay, we have our 7 indicator. We follow right across, and we find it right up. Oh, I drew it to the wrong one. Oh, no. Okay, now what we end up seeing here is we see it turn bright blue, so it is looking like it's somewhere on this side in our pH range. Okay, again, it implied based on our phenolphthalein, we're somewhere over here as well. Now, if we take a look at methyl orange, okay, we find methyl orange down here. It's our third one. Okay, we end up seeing it go from a range of roughly about 3 to 4 point something. Okay, and again, we see the yellow-orange color right here. Okay, it kind of goes in the yellow-orange area right here, which implies it is greater in the base area. Okay, it could be acidic, but since all of these guys up here are implying a base, I'm going to go ahead and say it's over 7.
Cool.
I would say even over 8.
And that's all we would expect you guys to do. We'd expect you to be able to classify it as a base with some indicators, and we're going to get you using ones other than litmus so that you're familiar with them. If we were to run through the other example really quick, the other unknown, number 2, we could do a similar process. Going to put in my 7 line for acid-base determination. Phenolphthalein is on the colorless side, the first one here. The second one is the bromothymol blue, who is yellow, so that means he's over here. And the third one is still methyl orange, and he's kind of a reddy orange color. So if he's reddy orange yellow, I could just say he's somewhere in here. Because you guys don't need a pH, we're actually just going to say, you know what? These things are all kind of saying this way, this way, and this guy is actually somewhere in here. This should be a pH around 4 or 5. This should be an acid.
Done and done.
Let's see how we did. Answer key. Super fuzzy. If you can read that says pH of 10. Confirmation. This line was a base. This one was a pH of 5. This guy was acidic. Now, was he very acidic at 5?
No.
But good enough to be called an acid. Other methods of pH determination.
Okay, you can use a pH meter or a pH probe. These are something you're going to probably use in Chem 20. They're really easy since you don't have to judge colors, you don't have to judge anything like that. It gives you a nice reading of pH without using litmus paper, without using other indicators like that.
And the other one that's kind of fun is pH paper. Now, pH paper is interesting. It's like litmus paper, but it shows you lots of different pHs. The reason we don't use it too much is sometimes on some pH papers, brown means 2 or 13. That's not a very good thing. If we have something that is either very acidic or very basic, we need to know which one it is, not be left guessing. So we don't use pH paper very often.
Acid-base neutralization. Properties of acids make them very dangerous and hard to handle and hard to clean up. Acids and base react with each other, like we've talked about already, in a neutralization process that produces a salt and water. Now, when we say a salt, it doesn't mean hitting somebody. It doesn't mean the regular salt you see on the table. It means an ionic compound for our Science 10 purposes.
Those jokes were terrible. All right, so we have acid, which is like H plus something, plus a base, which is like, I don't know, a base with some OH.
Huh.
Now, if I look at this, here's how I make water. And this actually links us to the idea of later of how we'll do reactions. If I was to take the H and the OH to make the water, that means the A and the B are feeling neglected. The acid and base come together and actually form the salt. That's not
an I, but good effort.
Oh, there we go. Okay, much better. Ladies and gentlemen, that's it for acid-base properties. You're going to practice this lots. We're going to look at reactions later on. And next we're going to get into naming. So you need to know what is an acid, what is a base, when you're actually looking at their properties.
And one last thing, Science 10. Stay classy.